Today I'm going to introduce you to a reaction having to do with chemical kinetics that you will be carrying out in the physical chemistry laboratory. The method of initial rates in the bromination of acetone. Here is the reaction we're talking about. It is of the reaction of acetone with molecular bromine to form brominated acetone plus hydrogen ion and bromide ion. This reaction you will carry out in the presence of catalyst, hydrogen ion, so that the reaction completes in a reasonable time in the laboratory. Now, a word about why you're doing an experiment on chemical kinetics. Characterizing the rate law of a reaction is an important step in understanding the reaction. If we know the rate law, we can predict how long processes will take under different conditions, and this can be important for industrial processes as well as for academic research. So here we have the rate law for this particular chemical reaction. The rate of reaction, which is capital R, can be written as this product. K is the rate constant, P is the order of reaction with respect to hydrogen ion, likewise Q and R for the orders of reaction with respect to acetone and bromine. Take a step back for a moment. Not all rate laws are this simple. So one usually learns in general chemistry that the rate law is a rate constant times each of the reactants to some integral power. In this case, we have a catalyst raised to a power as well as reactants. In other cases, the rate law may not even be capable of being written as a product of concentrations to powers. The more complicated the rate law generally, the more complicated the mechanism, which means the series of elementary reactions that occur to give the overall rate law. Well, we have chosen a relatively simple reaction for your investigation, and a few things are known in advance. One, we know that the order of reaction with respect to bromine is 0, which means in essence that bromine does not enter the rate law at all. So you can write the rate law in this simplified fashion. Second, it is known experimentally that P and Q are integers. So when scientists investigate chemical reactions, they usually begin with the assumption that the rate law is simple and that the orders of reaction are integers until they have very strong evidence to the contrary. So we're going to begin with that assumption, and our time only allows us to follow with that assumption. Okay, it's a reasonable starting assumption for any reaction. Okay, so you will assume that P and Q are integers. So what you need to determine are the rate constant K and the orders of reaction P and Q. So the theory for measuring the rate. You know from prior study that one can measure the rate by measuring the rate at which products are formed or reactants are consumed. So you can choose any reactant or product to measure the rate of reaction. Now we have chosen bromine because it's convenient. One can measure spectrophotometrically the concentration of bromine by the absorbance at 400 nanometers. Okay. None of the other reactants or products or the catalyst absorb at 400 nanometers. So by measuring the concentration of bromine with time, we can measure the rate of reaction. Now, the theory for determining the orders of reaction P and Q. As you can read in the lab manual, P is the partial derivative of the log of the rate with respect to the log of the hydrogen ion concentration when the concentration of acetone is held constant. The reason, of course, that bromine does not also have to be held constant is that bromine's order is 0. Likewise for Q, Now we have the partial of the log of R with respect to the log of the acetone concentration if the hydrogen ion concentration is held constant. So we have theories then for determining K, P, and Q from experimental data. So what are we going to measure precisely, and what will our data look like? So the experimental data. You're going to create a set of solutions. You'll create 7 solutions using hydrochloric acid, acetone, deionized water, and bromine. What you will do is first create stock solutions of particular concentrations. Those are listed in the blue at the top there. And then using those stock solutions, you will create 7 solutions with varying concentrations of the individual species. Now notice that the total volume is 50 milliliters in every case. That will make the calculation of the concentrations of each species simple. I want to remind you to record the temperature when you do the reaction, and that's because the rate constant depends on the temperature. Now, as you construct your solutions from the stock solutions, the individual solutions from the stock solutions, you will proceed in the following manner. You will first add the HCl and the acetone and the deionized water all together, very carefully using volumetric pipettes. And then just before you're ready to carry out the reaction, you'll add the bromine. Reaction begins only once you add the bromine, and you'll then begin to follow the concentration of bromine spectrophotometrically by placing your sample in the spectrophotometer. Now notice that 4 of these solutions have the same amount of acetone and hence the same concentration of acetone. A different set of 4 solutions has the same concentration of hydrogen ion because the concentration of HCl is the same. So we will use the method of initial rates. We're holding the concentrations of a particular species to be the same in a given set of solutions. Now, in fact, not only are the starting concentrations the same of hydrogen ion and acetone, but they really don't change significantly during reaction. I'll demonstrate that with the next bit on this slide. So here we have an example of solution 1, and I'm showing you the units of molarity for hydrogen ion, acetone, and bromine. As we have the initial concentration and the final concentration. By final, I mean after reaction is complete. The bromine will be used up. Of course, there's a tiny bit left because no reaction goes to completion, but this one goes so nearly to completion that the bromine is essentially undetectable at the end. Now, the hydrogen ion concentration, then you can see, will be 1 molar times 10 mils divided by 50 mils, the total volume, and that gives you 0.2 molar. And the same calculation, kind of calculation shows you that acetone's concentration is what you see here, and bromine's this. So if the bromine gets used up, because the stoichiometry is 1 to 1 to 1, the concentrations of hydrogen ion and acetone hardly change at all, at least in relative terms. So those concentrations are nearly constant. Okay. This allows us to determine the rate for each solution and determine P and Q and K. Okay. So what are we going to do? So what you will do first is, for solution 1, plot absorbance versus time. Remember, absorbance is proportional to the bromine concentration, so the slope then will give you the rate. You'll have to use equations in the lab manual. And likewise for solution 2, from the slope, you will be able to determine the rate. The slope does not equal the rate, but the rate is determined from the slope. Likewise for solutions 3 and 4. Those 4 solutions have the concentration of acetone held constant. So in step 2, you will plot the log of the rate versus the log of the hydrogen ion concentration, and the slope then gives you P. Now, because they're scattering your data, your P may turn out not to be an integer, but we are making the assumption that the actual P is an integer, and so you should round whatever number you get to the nearest integer. Okay. To the extent to which this is not an integer represents experimental error. Then you do the same kind of thing for Q, only you'll consider the solutions in which the hydrogen ion concentration is held constant. Lastly, to get the rate constant K, what you will do first, for example, for solution 1, you can plug the rate and the P and the Q into the rate equation, and from that you'll be able to deduce the value of K. You'll be able to do the same thing for solution 2. You'll get another value of K. In principle, they should be the same, but you'll have experimental error, so they won't be quite the same. Proceed along for all 7 solutions. You'll have 7 values of K. The average is your best value, and from the scatter, you'll get the uncertainty. So that concludes the description of the theory behind the experiment and how you will calculate the unknowns, the K and the P and the Q, from your experimental data.
Hello students. Today we will talk about experiment on kinetics of bromination of acetone. This experiment uses the method of initial rates to measure rates of chemical reaction of bromination of acetone catalyzed by hydrogen ions in the form of hydrochloric acid, and these measurements are made with different concentrations of different reagents such as acetone, bromine, and catalyst, which is hydrochloric acid. So to prepare this experiment, we need to prepare 7 different solutions of the mixture of hydrochloric acid, acetone, and bromine, which will be different in concentrations of hydrochloric acid and acetone. We use this glassware to prepare these solutions. The first step is to prepare stock solutions of hydrochloric acid and acetone, which are done by mixing certain amount of hydrochloric acid or acetone in volumetric flask and adding deionized water to the mud. Once stock solutions are ready, we prepare 7 different solutions of hydrochloric acid and acetone. We use this glassware to prepare these 7 different solutions, and we use these volumetric pipettes to add different amounts of hydrochloric acid and acetone. In first 4 solutions, we add fixed amount, 10 millimeter of acetone solution and different amounts of hydrochloric acid. In solutions 5, 6, and 7, combined with solution number 1, there is a fixed amount of acetone and different amounts of hydrochloric acid. In such a way, we have 4 solutions which have constant concentration of acetone and different amount of hydrochloric acid. And in the same way, we have 4 different solutions with fixed amount of hydrochloric acid and different concentrations of acid. The reaction of bromination will start immediately when bromine solution is added to our mixture. You can see that bromine, which was prepared in advance of this experiment, although you can prepare it by yourself if you follow the lab manual. So once bromine is added to the solution of acetone and hydrochloric acid, the bromination reaction of acetone immediately begins, and in this reaction, one H atom in acetone is replaced by bromine atom. Okay? So CH bond is broken and CBr bond is formed, and in solution, this is done with the assistance of hydrogen. How we will see that reaction take place? You can see that bromine solution has a characteristic yellow-brownish color. Once bromine is consumed in the reaction, the solution will lose its color and becomes transparent. So when reaction is complete, yellow color is fully gone. Therefore, we can follow the reaction progress using UV visible spectroscopy. The characteristic wavelengths at which bromine solution absorbs light is 400 nanometers. So the larger the concentration of bromine, the larger absorbance at 400 nanometers, according to Beer-Lampe law. Therefore, if we follow absorbance at 400 nanometers as a function of time, we can plot concentration of Br2 in the solution as a function of time, and in such a way we can determine the reaction rate, which will be the slope of the plot of absorbance and hence concentration of bromine as a function of time. Well, this is an old-fashioned but rather reliable UV visible spectrometer, and we can set it up for particular wavelengths. So you can see now 400 nanometer wavelengths set up, and we can switch between transmittance and absorbance mode. We will work in absorbance mode when we put our cuvette with the sample inside the spectrometer. So cuvette goes here, we close it. Of course, before we start our measurements, we need to set up the spectrometer, and this is done initially in transmittance mode. We will need set transmittance to 0. First, we need to set transmittance to 0 without order. We need to remove anything from here, and we are setting up transmittance to 0. And then we will need to insert blank. This is deionized water. And here if we are in transmittance mode, we need to set transmittance to 100%. To 100. Or if we are in absorbance mode, it needs to be set to 0. So now our spectrometer is ready. Okay, so now we have our stock solutions ready, and we already mixed 10 milliliters of HCl stock solution, 10 milliliters of acetone solution, and 20 milliliters of water, which corresponds to our solution number 1. So the next thing to do, we will need to add bromine. Okay, so now we are prepared to add 10 milliliters of bromine into our solution of acetone and hydrochloric acid. So the pipette, 10 milliliters. Now our solution is ready, and we need to quickly transfer it into cuvette because the bromination of acetone reaction starts immediately after the mixture is made. And now we can start timer, write down the first absorbance, and take measurements every 30 seconds. Well, you can see that absorbance doesn't change anymore, which indicates that the reaction is completed, so we can stop our timer. Bromine, which was in the mixture, is fully consumed, and the reaction stopped because there is no more Br2 reagent. If we take out our cuvette, we can see that our solution is now transparent. The yellow color is gone, disappeared. So Br2 reacted to brominate acetone and disappeared from the solution. After we finish our experiments for all 7 solutions, we need to clean our glassware. We need to put waste in waste containers. There are 2 waste containers in the lab. One is for non-halogenated solutions, and the second one is for halogenated solutions. The solution of acetone goes to non-halogenated waste, but all other solutions you made, they have either HCl in them or brominated acetone, and therefore they go to halogenated regular paste. So to finish the lab, wash all the glassware, put them into their correct places, to the shells, and this is it.